Hello everyone. Today I will discuss about different type of metamorphic reactions. I will cover this topic under the following heads: introduction, type of metamorphic reactions, phase transformation, X solution, solid-solid net transfer reaction, devolatilized reaction, continuous reaction, discontinuous reaction, ion exchange reaction, redox reaction, reaction involving dissolved species, reaction and chemographics, and lastly conclusion. Metamorphic reactions are very important to understand the different textures and new set of minerals which are stable under the new condition of pressure and temperature. Normally, prograde metamorphic reactions involve dehydration or decarbonation. The large increase of entropy that evolve the liberation of volatile phase from a mineral indicates that rising metamorphic temperature will favor reaction that produce separate vapor phase. The reaction among solid and fluid phase can be classified in various types based on what the reaction does, how the reaction progress, or on the basis of different phases evolved. A metamorphic reaction is an expression of how the minerals got their final state, but a reaction does not necessarily tell us the path that was actually taken to arrive at this state. Sometimes it is possible to deduce the path by means of a reaction mechanism. Thus, we will also explore reaction mechanism if we are considering a rock of fixed chemical composition. Then a metamorphic reaction states the principle of equilibrium. In other words, if we can write a reaction expressing equilibrium between the minerals we see in the rock, we expect that the reaction must have taken place during metamorphism. If we treat isograde as reaction, we can understand what physical variables might affect the location of a particular isograde. Affect isogrades, we may also be able to estimate the PTX condition that an isograde represent. Let consider a rock having fixed chemical composition. Then a metamorphic reaction state the principles of equilibrium, that is equilibrium between the minerals. The various type of metamorphic reactions are as follows. First, phase transformation. Phase transformation, the polymorphs of SiO2 or Al2SiO5 or graphite, diamond or calcite aragonite, Al2SiO5, graphite and calcite are the simplest to deal with. The transformation depend on temperature and pressure only. Phase transformation is also known as discontinuous reaction, which occur at a particular temperature and pressure. For these reactions, a curve or line can be drawn on a pressure temperature diagram. For example, kyanite give rise to selemonite or calcite give rise to aragonite and graphite give rise to diamond, etc. Products and reaction can only be coexist stably precisely at equilibrium reaction condition on the reaction line in PT space. Discontinuous reactions are always net transfer reaction. Little driving force for phase transformation to produce common metastable relics of one polymorphs in the stability field of another. Coexisting polymorphs may therefore represent non-equilibrium states. Second, exsolution. Exsolution phenomena we can observe in plagioclase. Normally perthite and antiperthitic texture is formed in alkali feldspar with intergrowth of one into another. Solid-solid net transfer reaction. The solid-solid net transfer reaction, also known as solid-solid reactions, occur among solid phases, involve solids only of different composition. These phases may include elements found in fluids, hydrogen, carbon, but those elements are considered in the solid phases, so that no fluid phases H2O or CO2 are involved as reactant or products. Solid-solid net transfer reactions can be continuous or discontinuous, and they may be terminal or tie-line flip reactions. They normally differ from polymorphic transformation. The solid-solid reactions plot on the PT diagrams as essentially straight lines. This is because the delta S and delta V of the reaction do not change much with varying pressure or temperature. To the extent that delta S and delta V do change with pressure and temperature, they change about the same amount for both the reactants and the products. For examples, NaAl Si2O6 plus SiO2 give rise to NaAl Si3O8, that is jadeite plus quartz give rise to albite. Second, Mg2 SiO2 plus inositite plus anorthite give rise to diopside plus andalusite. 4, MgFeSiO3 plus CaAl2 Si2O8 give rise to MgFe thrice Al2 Si thrice O12 plus CaMgFe Si2O6 plus SiO2. Orthopyroxene plus plagioclase give rise to garnet plus CpX plus quartz. If minerals contains volatiles, the volatile must be conserved in the reaction so that no fluid phase is generated or consumed. For example, the reaction Mg3 Si4 O10 OS twice plus 4 Mg SiO3 give rise to Mg7 Si8 O22 OS twice, that is talc plus inositite give rise to anthophyllite. Involves hydrous phases but conserve H2O. It may therefore be treated as a solid-solid net transfer reaction. When solid solution is limited, solid-solid net transfer reaction are discontinuous reactions. Discontinuous reactions run to complete at a single temperature and a particular pressure. There is thus an abrupt discontinuous change from the reactant assemblage to the product assemblage at the reaction isograde assemblages. Devolatilization reactions are net transfer reactions that involve the liberation of a volatile phase H2O for dehydration reactions or CO2 for decarbonation reaction. Examples of dehydration and decarbonation reactions are muscovite plus quartz give rise to potash feldspar plus limonite plus water. Dehydration depend upon the partial pressure of water. Another reaction is your calcite plus quartz give rise to wollastonite plus CO2, that is a decarbonation reaction, because the entropy of a fluid is generally greater than the entropy of the solid phases. Fluid appear on the high temperature side of most such reaction. If the fluid composition is fixed, then devolatilization reactions are discontinuous. But if the fluid composition can vary as a result of the liberation of H2O or CO2, then the reaction will be continuous reaction. For example, KAl2Si3 AlO10 OS twice plus SiO2 give rise to KAlSi3O8 plus Al2SiO5 plus H2O. Muscovite plus quartz give rise to potash feldspar plus sillimanite plus water. Suppose H2O is withdrawn from the system at some point on the water saturated equilibrium curve. Therefore, P water equal to P lithostatic pressure. According to Lister principles, removing water at a equilibrium will be compensated by the reaction running to the right, therefore producing more water. This has the effect of stabilizing the right side of the reaction at the expense of the left side. So, as water is withdrawn, the potash feldspar plus sillimanite plus water field expand slightly at the expense of the muscovite plus quartz field, and the reaction curve shift towards lower temperature side. Curvature. The curves for the dehydration or decarbonation reaction on the PT diagram will have shallow slopes at low pressure, because volume of a fluid phase is much larger than that of the solid phases. However, the compressibility of a fluid lead to a rapid decrease in the volume as pressure rises. So, the slope is steepened with rising pressure, leading to substantial curves. Some reaction curves around and gain a negative slopes at high pressure. Sensitivity to fluid composition. The PT position of a decarbonation or dehydration reaction change for a dehydration reaction such as muscovite plus quartz give rise to potash feldspar plus sillimanite plus water. If the rock contains an H2O rich fluid, the right hand side of the reaction will be stable over a smaller range of condition than if the rock contain an H2O poor fluids, either because the fluid is diluted with CO2 or the rock is derived out and not fluid saturated. Mixed volatile reaction involve the liberation and or consumption of the more than one volatile phase, typically H2O and CO2. An example is tremolite plus calcite plus quartz give rise to diopside plus H2O plus CO2. Mixed volatile reaction have the same general shapes as dehydration and decarbonation reaction on PT diagrams. However, they are generally plotted on temperature composition diagram instead of pressure temperature diagrams. Terminal reaction involves the creation of a new phase from two or three other phases, or in the other direction the decomposition of one phase into two or three others. They may be solid-solid reaction or they may involve a fluid phase. An example of a terminal reaction is chloritoid give rise to stolite plus garnet plus chlorite. Tile and flip reaction. The tile and flip reactions involve two phases becoming stable together that were previously unstable together. And as with terminal reactions, they may be solid-solid reaction or they may involve a fluid phase. An example of a tie-line reaction is chlorite plus garnet give rise to biotite plus restorolite. Continuous reaction involve phases that may be vary in composition. Such reactions are more common than discontinuous reaction because compositional variation of either fluid or solid phases is typical for geological materials. Continuous reaction occur over a range of conditions so that the products and reactant coexist stably over a range of conditions, but the composition of the phases changes systematically as condition changes. Continuous reaction may be net transfer reaction or exchange reaction. Continuous reaction involve members of a solid solution series. The partitioning of the chemical elements between phases changes progressively during reactions over range of P and T or with the production of new phases. For example, calcium rich garnet grow accompanied by a reactant in anorthite content of plagioclase as it reacts and fractionate into the garnet. Continuous reaction occur when the reactant and reactants products coexist over a temperature or grade interval. The composition of solid solution phases vary across the interval and the proportion of the mineral changes until changes one of the reactant disappear with increasing rate. Discontinuous reactions are those that occur at a particular temperature for a particular pressure. For these, a curve or line can be drawn on a pressure temperature PT diagram. Kyanite change into selemonite, reaction on the phase diagram on the either side of the curve. A different set of phases is stable in a discontinuous reaction. Products and reactant can only coexist stably precisely at the equilibrium reaction condition on the reactant line in PT space. Discontinuous reaction are always net transfer reaction. This is also known as exchange reaction, involve two phases that both share a solid solution exchange, such as sodium by potassium or Fe+2 by Mg. For example, garnet FeMg thrice Al2 SiO4 thrice and biotite K potassium FeMg thrice Si3 Al O10 OS twice. Reactions of these types are all continuous and differ from the other kind of reaction. The curve of these reactions are straight on a PT diagram and very steep because no change in volume. The reaction can be written as almandine in garnet plus phlogopite in biotite give rise to pyrope in garnet and enite in biotite, expressed as pure end members, but really involve FeMg or other exchange between immediate solution. Basis for many geothermobarometers causes rotation of tie line on compatibility diagrams. Redox reaction involve a change in oxidation state of an element. For example, 6 Fe2O3 give rise to 4 Fe3O4 plus O2. Second reaction, 2Fe3O4 plus thrice SiO2 give rise to 3Fe2SiO4 plus O2. At any particular pressure, these become oxygen buffer. Minerals plus ions plus neutral molecules dissolved in a fluid, example is hydrolysis. For example, 2KAlSi3O8 plus 2 hydrogen ions plus water give rise to Al2Si2O5 OH4 plus SiO2 plus 2K plus potash feldspar plus aqueous species give rise to kaolinite plus aqueous species. Reaction in chemographics. We can use chemographics in inferred reactions. For example, see the straight line on the screen where we can see the MgO, periclase, phosphorite, inositide and quartz. Now we can see how many possible reactions are occur. Say for example, FeO, that is phosphorite plus quartz give rise to inositide, Mg2SiO4 plus SiO2 give rise to Mg2Si2O6. Second reaction, inositide plus periclase give rise to phosphorite, Mg2Si2O6 plus 2MgO give rise to 2Mg2SiO4. Next reaction is periclase plus quartz give rise to phosphorite or inositide. If we know the chemographics, we can determine that a reaction is possible. What reaction is possible between A, B, C, D? See the diagram on the screen, the triangular diagrams where we can see the tie line between A, B and D and another phase that is C also in a triangular diagrams. Now we can see a chemographic diagram for some metamorphic zones. As per the diagrams A, B, C, now A and B react and give rise to C plus D at the isograde. See the diagrams second where we can see the new tie line developed between C and D. It means A and B react and always there will be a cross tie line if the components within the system. Therefore, A plus B react and give rise to C plus D. Now, see the diagram where we can see the new tie line developed between C and D. In this module, I have discussed in detail about the metamorphic reaction, which are very important to understand the different texture and new set of minerals which are stable under the new condition of pressure and temperature. The whole topic I have covered under the following heads, that is about the net transfer reaction, exchange reaction, discontinuous reaction, continuous reaction, solid-solid net transfer reaction, polymorphic reactions, devolatilization reaction, mixed volatile reactions, terminal reaction, tie line flip reaction, ion exchange reactions, with example to understand the different metamorphic reactants and its significance to understand the metamorphic reaction and textures which are stable during new set of P and T conditions.